So today I'll present work by me and Dr. Nigel Ward. This work is called Using Prosody to Spot Location Mentions. And this is for the Speech Prosody 2020 conference held virtually this year because of the coronavirus. First of all, we want to find when someone says a location in speech. So if someone says the United States of America, we want to find when in the audio they actually said this. Location finding is actually important for information retrieval, summarization, and translation. For summarization, you can imagine that if you want to summarize what someone said, you may want to find the location. This is because, as you can imagine, locations have a lot of semantic information that goes along with them. So usually it's important to include these in the summary. The other thing is translation. Let's say you want to translate something like El Paso. When you translate it from Spanish to English, you'll actually see that it doesn't translate it correctly because El Paso, if we know that it's a location, then we can translate it differently. But if we don't know that it's a location, then it'll just translate to something like step, which is incorrect. And so that's one of the main reasons why location spotting is actually important. So the standard method to actually find locations is to use a speech recognizer and a gazetteer. A speech recognizer takes in the audio signal and translates that audio signal into text. And a gazetteer, you can imagine, in this context, is just a list of locations. So here in this diagram, for example, we take in the audio signal, we use the recognizer to translate into text, and that text, we check in the gazetteer whether it's a location or not. If it's in the gazetteer, then it's a location. If it's not in the gazetteer, then it's not a location. But there's some limitations with this method. Some are that the speech recognizer might have out of vocabulary words, and it might not actually have the location in the vocabulary. In that case, it won't get the location. Another problem may be that you might be dealing with a low resource language. In that case, there might not be a speech recognizer, or the speech recognizer might be very limited. So the gazetteer might not have all the locations. So you can imagine that little rivers or mountains won't actually all be in the gazetteer. And so in that case, this method can't actually find the location. So the proposed method is to actually use prosody. So prosody is, you can imagine, the intonation, the stress, the rhythm of how you say something. So instead of looking at what is being said, we can look at how it's being said. So here I have an example audio where we ran low pass filtering. And so it's harder to understand what is being said, but now you can just focus on how it's being said. So here I'll play it.
I don't know, let's put it that way. Yeah, but that hasn't reached Richardson yet, huh? No, thank goodness.
And from the audio, you can kind of tell where the location should be. So the standard method I talked about doesn't actually use prosody. It uses a speech organizer and it turns it to text. But prosody might actually be useful in this task because previous work has shown prosody can help in spotting named entities. And since all locations are named entities, then prosody might help. The other reasoning is, depending on the function of what you're saying, so maybe I'm asking a question or maybe I'm agreeing, there may be different prosody. For example, how are you? As opposed to yes. So now you can imagine that we have spontaneous speech that comes in, and now we want to find out which of these frames are locations and which ones aren't. And that's our task. The target is 1 if it's a location, and we want to predict 0 if there's not a location. Every 50 milliseconds in the audio is going to be a frame. And we want to classify each of those frames as a location or not a location. So for data, we're actually going to use the switchboard corpus. You can imagine this is conversations between two people over the telephone talking in English. The advantage is that there's a lot of this data, around 200 hours. The data all has transcriptions that are word aligned, so you know when a word started being said and when they stopped saying that word. And there's also a lot of locations in this data, and so it's actually really useful for this task. Here I'm going to play an audio clip of the data so you can get an idea of how it sounds like.
And you could get it real cheap when it was green.
Oh.
So that was the trick. Where do you live?
I live in Sherman now. I'm from Indiana.
Oh, okay.
So you can imagine that's how the conversations go. So we're going to do supervised learning to actually run this task. So we're actually going to build 2 models. A linear regression model, because linear regression models are easy to find out what it's learned, since we can just look at the coefficients. And a long short-term memory model, since it's been shown to work well in speech tasks. So to summarize, we have speaker A, we have speaker B. Their conversations are recorded. We're going to compute the prosodic features of those conversations. So you can imagine we have the pitch, intensity, voicing. We're going to concatenate all those features. And then we're going to use all those features to train a model. And the model is going to predict a range between 0 or 1, whether there is a location or not. And hopefully closer to 1 if it's a location, and closer to 0 if there's not a location. So now which features are we going to use? For linear regression, we used features that span a range of 3200 milliseconds before the frame we were going to predict, and 3200 milliseconds after the frame we're going to predict. And so now we have this context, and so we know what's happening in the past and the future. And these are the features that we're going to actually use listed here. And we're going to use more features in linear regression than LSTM, because we can assume that the LSTM is actually going to learn a lot of these features that we're actually going to give to the linear regression model. We're also going to compute the features for both of the speakers. So both speaker A and both speaker B get the features and are going to be used to make the prediction. So the locations are actually not labeled in the transcripts. We don't know which words are locations. We know exactly what's being said, but we don't know which of those words are locations. And so we actually use the natural language processing library called Spacy to find which of these words are locations. But sometimes Spacy can make a mistake. For example, on one of the places where it failed, it classified the word Dallas in Dallas Cowboys as a location, even though it really shouldn't be considered a location, because with broader context, it's actually an organization or a team name. And so we actually did a small evaluation to see how well Spacy is doing. So we hand annotated 100 locations, and then we computed the precision and recall. We found we got a precision of 88% and a recall of 86%. So there was some noise in the data, but we still thought it was adequate enough for training and for testing. So the first model was the linear regression model, and we trained it to predict whether there's a location or not. As you can imagine, locations are not that common in speech. Only 1 in 256 frames are actually ended up being locations. And since there's a huge data imbalance, to train the model, we actually downsampled so that 50% of the frames are locations, and the other 50% of the frames are not locations, but have speech. And so then we trained on 70% of the data, tested on 15%, and used the other 15% as a def dataset. So we actually used the threshold. If the prediction was lower than threshold, we set the value to 0. And if it was higher than threshold, we set it to 1. And so using 50% of the def dataset, we got a threshold. We maximized the F1 measure, and then we used that same threshold for the test dataset. And these are the results that we got. So the precision was higher than our baseline, which was 50%. And this was the recall and the F1 measure. Next, we wanted to use an LSTM model. LSTM is actually a recurrent neural network model that takes in a sequence of data. So for each frame, we feed it the prosodic features, and the model itself outputs a prediction for every frame. And so we fed the LSTM model sequences of 10 seconds of data. And as you can imagine, we still had the previous problem where there was a data imbalance. And so to reduce this data imbalance, we actually only fed it 10 seconds of data sequences that had a location. This actually turned the data imbalance from a 1 in 256 being a location to 1 in 14, which we thought was a lot better for testing and training. And so this table actually shows the results when comparing to the previous data set I mentioned, where half of the frames are locations and the other half are frames without locations but with speech. And these are the results that we got. And again, we see that we got above 50% precision, which was above the baseline. And this is the LSTM architecture that we got when optimizing over the dev dataset. So now that we evaluated over the data subset where half of the frames are locations and without locations, we can actually compare the models, and we see that they have very similar F1 measures. So both the LSTM and the linear regression perform very close, and the precision was the same for both of the models. Next, we actually wanted to find out how well our LSTM model was actually doing. So for the LSTM model, we actually computed 3 baselines to compare the LSTM results to. So you can imagine we have the audio signal, and we have text that aligns with it. So our first baseline was actually very naive. It was a random baseline that just predicts 0 or 1 randomly, and it doesn't look at the audio signal at all. And so this was the first baseline that we compared to. The second baseline that we made was the speaking baseline. And this baseline always predicts that there's not a location mentioned when there's silence or no speech. And so you can imagine that this one performs a lot better than the random baseline. And this baseline predicts 0 or 1 randomly when there is speech. As you can imagine, since there might be a lot of silence in the audio files from the other person not speaking, then this baseline is actually going to perform a lot better. The next baseline was the content word baseline, and this baseline only predicted randomly when the content word was being said. And it predicted that there was not a location when there was a function word being said or there was silence. And so to find out whether there was speech or not, we actually used the word line transcripts. And to find out if there was a content word or not, again, we used the word line transcripts, and we used an NLTK stop list to find which of these words were function words. Next, we evaluated on the data where every 10 seconds sequence of data actually has a location. And we computed the same thing for all 3 baselines. And so as you can see, our LSTM model actually outperformed the random baseline, the speaking baseline, and the content word baseline. So our content word baseline actually used the transcript to find out whether there was a content word or not. And so our LSTM model was actually able to outperform this baseline model that actually knows perfectly whether there's a function word or content word. So we can say our LSTM model performs better than knowing whether there's a content word or a function word. So this tells us that prosody is actually informative. And so these were really good results. So as you can remember, we were actually feeding the features of the speaker A and prosodic features of speaker B. This is because maybe the LSTM could learn from the other speaker's features, or it could also correct from cross-track bleeding. And so we expected features of both speakers to have better performance than features of just one speaker. We actually wanted to find out how informative the prosodic features of the other speaker were. And so we trained an LSTM model with the prosodic features of both of the speakers, and an LSTM model with just the prosodic features of one of the speakers. And we actually found out that having the prosodic features of both speakers was not actually that useful. We got very similar results with the one speaker LSTM actually outperforming the two speaker LSTM. And so that was surprising to us. So the results suggest that interlocutor features are actually not very informative in this task. Next, we wanted to find out if the model is actually location specific. So are we actually detecting location specifically, or are we just differentiating between named entities and not named entities? So it could be that our model is just finding out if there's a named entity or not a named entity, and the model might not be specific to locations. And so to find out if our model is actually location specific, we got both of the means. As you can see from the PowerPoint, we got a higher mean on the location frames, and we ran a t-test to find out if our model is predicting higher on location frames than on named entity frames. And we found out that it was statistically significant. So we actually found that we are predicting higher on location frames than on named entity frames. And here we also plotted a histogram, and so we can see that on higher prediction values, like on the dotted threshold line, we're actually having a higher prediction for locations than named entities. And before the threshold, named entities are actually having lower predictions than the threshold, than locations. So next, we actually wanted to test our model on different languages and different genres. So one question that we had was, is there shared prosodic patterns between languages? So maybe the prosodic patterns of how you say a location in English are similar to how you say a location in Spanish. And so we actually compared on a few data sets: English news, which you can imagine is just one person speaking; switchboard data, which is what we trained on; Japanese conversations; and Spanish conversations. So we tested our model on these data sets. We got 100 of the highest predicted time points, and we computed the precision. And so to compare, we actually computed two baselines: the speaking baseline, which was 100 time points that were random that had speech, and this was hand annotated; and a content word baseline, which was 100 random time points that had content words being said. So we computed the baselines, and we outperformed the baselines in English news, switchboard, and Spanish call home. But for Japanese, we actually did not do better than baseline. This was a very small scale experiment, and so these results don't indicate that there might be cross-language shared prosodic features. Next, we actually got a feature analysis from the linear regression model. We can actually find out which features are actually important in predicting a location. So in this figure, black indicates that there's a positive correlation, and white indicates that there's a negative correlation. And the thicker the line, the stronger the correlation. And so we plotted this, and here you can kind of see which features are actually important. So here I'm going to play an audio file that actually matched a lot of these features, and that actually does have a location.
Go nowhere up north, nowhere.
Doesn't go anywhere north of the Red River.
I don't even want to go anywhere. Yeah, that's about it.
So the location you could hear was Red River, and a lot of these features actually matched. Next, we did a failure analysis. We got 20 false positives where our model predicted the highest when there actually wasn't a location. And so looking at these, 7 were actually very close to being locations. So they were half a second off from being a location. 2 were actually sports teams, and 2 were actually locations being said in their interlocutor track. So next we identified 20 false negatives, but we didn't find any pattern in these. We also analyzed 20 of the strongest hits, so our model predicts really high, and there is actually a location at these places. We actually found that 7 occurred in questions, with 5 of them being actually the last word of the question, and 3 were actually answers to questions, and other 7 were actually just truly grounded location mentions. For future work, we would actually quantify how well our prosody model can actually work with the speech recognizer. We would also run a bigger cross-language study, and so we can find out which languages have shared prosodic patterns, and we would look into the value of shared network training. So in conclusion, we found out that prosody is informative for location spawning, and the LSTM model is actually able to perform better than just identifying function words from content words. And the LSTM model is actually better at detecting locations than detecting named entities that are not location. So our model is location specific. Thank you for listening.